Hello everybody, I hope you're doing well. Welcome back to another video in our probability review. So this video is going to be talking about the binomial, Poisson, and normal distribution. These three distributions are very cool, interesting, and special distributions used within probability theory. And there are numerous types of distributions that statisticians and probability theorists use day to day, but these three distributions are a good way to get our feet wet with special types of distribution. So, as you may recall in the previous video, we have talked about probability fundamentals, some basic properties of probability, and we've also talked about random variables. And we also discussed that when we're given data, we want to come up with distributions to help describe our data, right? In terms of stuff like skewness, we also could describe the average, we can also describe the spread of our data, etc., right? But today in this video, we're going to talk about some special distributions. And sometimes when you're plotting distributions of your data, you might be able to approximate your data with a known distribution with really special properties. So we'll be talking about the binomial distribution, the Poisson distribution, and the normal distribution. So without further ado, let's dive in. So the first distribution we're going to be talking about is the binomial distribution. So to set up our scenario for the binomial distribution, consider the following. So let's say we have n trials, right? N number of trials. Each trial has a success or a failure outcome. We will also assume that each trial is done independently, so that the outcome from, say, trial 1 will not affect the outcome of, say, trials 2, 3, 4, 5, and so on, right? So each trial can be broken up into a success or a failure, right? And a question we might want to answer is, given n number of trials, how do we find the probability of X number of successes, right? So say you have 10 trials, we want to be able to answer the question of, say, find the probability of 4 successes, right? Or any number of successes you desire, right? So we're going to have to go through a little bit of notation, right? We're going to let P be the probability of success, right? Because there's going to be a chance at which success occurs and there will be a chance at which failure occurs. So P will represent the probability of success. Now, since each trial is either successful or fail, 1 minus P will represent the probability of failure, as probabilities must sum to 1. So, given n trials and x successes, how do we figure out the probability of getting x successes? Well, you'll observe from our design that if you have n trials, you will get x successes. Since each trial is independent, P to the x is the probability of getting x successes. But wait, there's a catch. So, if you get x successes in your n trials, you must also get n minus x failures, right? By the very definition of running all n trials. So you'll actually have P to the x times 1 minus P raised to the n minus x. So 1 minus P is your probability of failure. Your n minus x here is the number of trials that resulted in failure. Oh, wait, there's more. We want any x number of trials to be successful among the n trials. So we need to find a way to quantify how many ways can you select x elements from a set of size n. Well, in this case, it doesn't matter the order in which the trials are successful. We just care about all possibilities in which there are x successful trials. So for example, if you have trials 1, 2, 3, 4, 5, one possibility of getting 4 successful trials is 2, 3, 4, 5. But you could also get trials 3, 2, 4, and 5 as being successful. But those are just the same 4 trials, right? So we don't care about the order in which the trials are successful. So in that case, we're going to use something called a combination, right? So we're going to insert this notation here, right? This notation is the combination. So we call this as n choose x. So this is going to be equal to n factorial over x factorial n minus x factorial, right? So n choose x represents the number of ways to choose x trials to be successful from a total set of n trials, right? So we'll need this term, right, to count for all possibilities of getting x number of successful trials from a set of n trials. So this is going to be the probability of getting x successes, right? So we summarize here, right? So we have that the probability, right, P of x will equal n choose x, P to the x, 1 minus P to the n minus x, right? Now, since we have a binomial distribution, we will also want to describe our expected number of successes, right? So the expectation of your binomial distribution happens to be a really nice formula. It's just simply n times p, right? So remember that n is the number of trials and p is the probability of success. And if you think about it, when we do this experiment a lot of times, so say you had 10 coins, right? And you're flipping them, right? And the coins are fair, so 50% chance of getting head, 50% chance of getting tails. If you flip a coin 10 times, right? And you repeat that over and over, intuitively, it seems like you're going to be expected to get 5 heads in the long run. And you'll notice that 10 times 0.5, the chance of getting a head is 5. So in this case, to generalize, the expected number of successes in a binomial experiment will be the number of trials, n, times the probability of success, p, right? And it kind of makes sense intuitively, right? If you think about a coin flip. Now, we also want to know about the variance, right? So the variance of a binomial distribution will be this. NP 1 minus P. So this is our formula for the variance of a binomial distribution. And you'll notice that standard deviation is simply the square root of the variance. So if we want to find the standard deviation, all we have to do is take the square root of this variance, right? So you would just take the square root of this NP times quantity 1 minus P. So now that we have the binomial distribution built out, let's discuss a few of these example problems. So in example 1, suppose we have a game where the goal is to find the hidden gem. And past data shows that the chance of finding the hidden gem is 10%. So we're going to sample 10 university students, right? And we want to find the probability that at least 2 students find the hidden gem when given the game, right? So let's show our work for problem 1. So for part A, right, we want to find the probability of 2 students finding the hidden gem. So in our case, when we're approaching this problem, we're going to define finding the gem as success, right? So 2 students finding the hidden gem means we want 2 successes among a sample size of 10 university students, right? So the probability of x equals 2 will be 10 students, choose 2, right? Times the probability of success, which is choosing the hidden gem, which would be 0.1. So you'll multiply by 0.1 squared. And the probability of not finding the hidden gem is 0.9. And if 2 students find the hidden gem, then 8 students did not find the hidden gem. So this is our probability of 2 students finding the hidden gem. So it's this expression. You can punch this into your calculator to find it, but it's good to have the expression. All right, let's move on to part B. So now, oh wait, I actually misread the question. We want to find the probability that at least 2 students find the hidden gem when given this game. So we found the probability that x equals 2, right? But we actually care about the probability of x at least 2. So what are the possibilities? Well, 0 students can find the hidden gem, right? So p of x equals 0 plus p of x equals 1 plus p of x equals 2, right? These are the possibilities of at least, hold on, sorry, my bad. We want the probability of x at least 2, right? So by our definition of probability, we don't care about scenarios where less than 2 students choose the hidden gem, right? So we're going to use our definition of probability, right? So the probability of at least 2 students finding the hidden gem is 1 minus the probability of x less than 2, right? So we want the probability of x less than 2. So that's just going to be simply p of x equals 0, right? Because 0 students could find the hidden gem, plus the probability in which 1 student finds the hidden gem, right? So to find the probability that x equals 0, let me chop this out since I misread the question. My apologies. So the probability in which x equals 0 will be, we want 0 successes, so that'll be 10 choose 0. The probability of finding the hidden gem is 0.1, 0 successes, and we have 0.9 chance of not finding the hidden gem, so we want 10 failures. So this is the probability of 0 students finding the hidden gem. The probability of 1 student finding the hidden gem, so 1 success, will be equal to 10 choose 1, 0.1 raised to 1, 0.9 raised to the 9. So now that you have p of x equals 0, p of x equals 1, you can plug it in for these two terms here, and you'll find the probability of x less than 2. So then now that you find this value, you will be able to find the probability of x greater than or equal to, because probability of x greater than or equal to is simply 1 minus p of x equals 0 minus p of x equals 1. So this is what we need to do to find the probability that at least 2 students find the hidden gem. Alright, next question. Find the probability that exactly 7 students find the hidden gem. So in this case, we want to find the probability of 7 successes. Well, we'll just use our formula, right? We have 10 students. We want 7 of them. We want 7 successes, so 10 choose 7 ways of that happening. The probability of success is 0.1, and we have 7 of successes. And the probability of failure is 0.9 with 3 failures. So this is the probability that 7 students find the hidden gem. Okay, part C. Let's find the expected number of students that find the hidden gem. And how about the variance? So in this case, the expected number of students who find a hidden gem is going to be NP. And since we have 10 students and the probability of success is 0.1, the expected number of students to find a hidden gem is 1 student. To find the variance, we'll just use our formula, right? So the variance is going to be NP 1 minus P, which will be 10 times 0.1 times 0.9, which will be 0.9. Punch into your calculator. So this is the variance. All right, that completes part C of question 1. So we work out question 2 next, right? So question 2 asks, suppose that you and your friends are enjoying fortune cookies at, say, a Chinese restaurant, right? There are 5 cookies handed to you. And according to the restaurant manager, the chance of finding a fortune in the cookies is 40%, right? What is the probability that at most 3 cookies contain a fortune? And we would also want to find the expected number of cookies that contain a fortune and about the variance. So let's tackle this question one part at a time. So let's find the probability that at most 3 cookies contain a fortune. So if x is a random variable representing the number of fortunes in the cookies, finding the probability of at most 3 fortunes is equivalent to finding the probability of at most 3 successes. We will define success as finding a fortune in the cookie to make our lives a little easier. So we want to find the probability that x is less than or equal to 3, where x is the random variable representing the number of cookies that contain a fortune. So the probability of x less than or equal to 3 can be thought of as the probability of x equals 0 plus the probability of x equals 1 plus the probability of x equals 2 plus the probability in which x equals 3. So we can compute each of these individual terms right here through using our formula up here. However, that's a little tedious though. We can observe that getting at most 3 fortunes in a cookie means we don't want scenarios where we get 4 fortunes or 5 fortunes, because remember we have 5 cookies, right? So this is equivalent to 1 minus the probability of getting more than 3 fortunes, right? And what are the ways of getting more than 3 fortunes in your cookie? Well, you can get 4 fortunes or 5 fortunes. So it's simply going to be 1 minus the probability of x equals 4 plus the probability of x equals 5, right? So all we have to do is find the probability of x equals 4 and x equals 5, which is a lot more tractable, right? So the probability of x equals 4 will be 5 cookies we have in total. 4 of them have to contain a fortune. The probability of getting a fortune in a cookie is 40%, and we have 4 such successes, and 0.6 is the probability of getting not a fortune, and we have 1 such failure, right? To find the probability in which you have 5 fortunes in all your 5 cookies, it's going to be simply 5 choose 5, 0.4 raised to the 5th, 0.6 raised to the 0, because if we have 5 cookies and all the cookies have fortunes, then 0 of them don't have a fortune, basically, right? So now we can compute this value and this value individually. You'll get p of x equals 4, p of x equals 5. You can sum these values together, and then 1 minus that sum will give you the probability in which you have at most 3 fortunes in your cookies. All right, let's find the expectation, right? The expected number of cookies containing a fortune. So that's going to be NP, and we have 5 cookies, and the probability of getting a fortune is 0.4, so that's going to be 2. So we expect 2 cookies to contain a fortune, right? Now let's take the variance, right? So the variance will be NP 1 minus P, right? So it'll be 5 times 0.4 times 0.6. So that'll equal 1.2 if we do our math correctly. So, yep, we have the variance, and we have the expected number of cookies that contain a fortune. So this concludes example 2 of the binomial distribution. Hopefully it wasn't too bad. Most of it is just using the formulas and your definitions of probability, and essentially using the formula for expectation and variance. And you'll see that a lot when we talk about the other distributions. Okay, the next distribution of interest is the Poisson distribution. And the Poisson distribution is a little bit interesting, right? The Poisson distribution is a discrete distribution just like the binomial distribution. If you notice, in the binomial distribution in our past examples, since we have a finite number of trials, we can actually enumerate all possible number of successes in a trial, right? The Poisson distribution is also a discrete distribution. And fun fact, the Poisson distribution is what the binomial distribution will approach as the number of trials increases. That part you don't really have to know. Let's just talk about what's the meat and potatoes of this. So in the case of the Poisson distribution, we have a variable called lambda, right? And it's going to represent the number of occurrences of an event in a given interval, right? And what we want to find is what is the probability of X number of occurrences in the interval. So this might sound a little bit abstract, but let's think. So here's a regular real world example which you can use the Poisson. So suppose you want to catch the bus, right? And we know that buses arrive at the bus stop every 30 minutes, right? So one bus comes every 30 minutes. And say that you're able to wait at the bus stop for 20 minutes, right? We want to be able to find a way to say, what is the probability that there will be a bus in 20 minutes, given that I know that one or two buses comes every 30 minutes. So this is the type of questions we can answer with the Poisson distribution, right? We care about the number of occurrences in a given interval. So what is this formula for the Poisson distribution? So the probability of X number of occurrences will be this value. So it'll be lambda raised to the X e to the negative lambda over X factorial. So you'll notice that lambda is the number of occurrences of an event in a given interval. And we will be given lambda in most of the problems we're going to do for our purposes. Lambda is a given. X is something that we are going to find, and the question will provide that to you. But this is the formula for the probability of X occurrences for a Poisson distribution. The expected number of occurrences, though, for a Poisson, fun fact, it actually is just lambda. And it turns out that the expectation and the variance of a Poisson are equal. So the variance of a Poisson distribution is just lambda. So the expectation and the variance are both lambda in a Poisson distribution. So now that we have a formula for the Poisson distribution and we have a formula for the expectation and variance, let's do some examples. So example 1. Suppose that we're trying to observe traffic accidents at a busy intersection. From prior research, you find that there are approximately 2 accidents per minute. And we'll observe this busy intersection over a 10-minute time interval. So part A, find the expected number of accidents in a 10-minute interval. So this is actually a lot easier than you think it is. So we know from the problem that there are 2 accidents per minute. So if there's 2 accidents per minute, there are 20 accidents per 10 minutes. So the answer to part A is just 20, right? There are 20 number of accidents in a 10-minute interval, given that you know that there are 2 accidents per minute. Now, let's find the probability that no accidents happen in the 10-minute interval. So we want the probability that no accidents happen. So we want the probability that X equals 0. X will represent the number of accidents. So we'll just use our formula for the Poisson distribution. So in a 10-minute interval, we know that 20 accidents happen. So lambda is 20. So we'll have 20 raised to the 0, e to the negative 20 over 0 factorial. You will also keep note that 0 factorial is 1. So this will be just e to the negative 20 over 1, which equals e to the negative 20. So since e to the negative 20 is an extremely small number, right, it doesn't seem very likely that no accidents will happen in the 10-minute interval, especially given our rate that 2 accidents happen per minute. Alright, part C. Find the probability that at most 3 accidents happen in the intersection. So we want to find the probability of x less than or equal to 3. So we can use similar tricks, right? So if there's at most 3 accidents that happen in the interval, we have these possibilities, right? P of x equals 0 plus P of x equals 1 plus P of x equals 2, right? These are the amount of accidents that could happen, right? In the case of having at most 3 accidents, right? And basically, to find P of x equals 1, P of x equals 2, P of x equals 3, you would use 20 as your lambda, and you would just plug into the formula, right? So this should be pretty straightforward. Okay, so now that we've taken care of problem 1, let's go over problem 2. Suppose that a bank has on average 3 bankruptcies filed per month. So over the course of 1 month, find the probability that exactly 4 bankruptcies are filed. Alright, so 2A. Alright, so when you read this question, let's identify what is the expected number of occurrences. So in the case of this problem, we know that there's on average 3 bankruptcies filed per month. That's like a rate, basically. So over the course of 1 month, we want to find the probability that 4 bankruptcies are filed. So essentially, we know that 3 occurrences occur per month. So in the course of 1 month, what is the probability of 4 occurrences happening, right? So we're going to let x represent the number of bankruptcies. So we're simply going to find P of x equals 4. Since we know that 3 bankruptcies are filed per month, we know that lambda is 3. So we're going to use our Poisson formula. So it's going to be 3 to the 4 e to the negative 3 over 4 factorial. So all you have to do is evaluate this, and this is the probability of having 4 bankruptcies in a given month, right? Okay, part B, let's switch gears a little bit. Over the course of 1 year, what is the probability that at least 1 bankruptcy is filed? Okay, so we know that there's 3 bankruptcies filed per month. So given that, how many bankruptcies do you think are filed per year? Well, 3 bankruptcies per month and 12 months are in a year implies that there are 36 bankruptcies filed per year, right? So lambda equals 36 for 1 year, right? So to find the probability that at least 1 bankruptcy is filed, we want the probability of x greater than or equal to 1. And we'll also know that this is simply 1 minus the probability of x equals 0, because we don't want 0 bankruptcies. We want at least 1 bankruptcy, right? So we're using our definition of probability here, right? So 1 minus the probability of x equals 0 would be 36 to the 0 e to the negative 36 over 0 factorial. So this will be the probability of at least 1 bankruptcy. So you can see e to the negative 36 is an extremely small number. So it's pretty likely that at least 1 bankruptcy is filed in the course of the year, right? So that takes care of 2b. Okay, over the course of a year, find the probability that at least 10 bankruptcies are filed. So we know that lambda is still 36, right? We found this out from part B. So we want the probability of x at least 10. So this is simply going to be 1 minus the probability of x less than 10. So this is going to be 1 minus P of x equals 0 plus P of x equals 1, right? I'm just listing out all the possible possibilities. P of x equals 9. So you can evaluate P of x equals 0, P of x equals 1, P of x equals 2, all the way to P of x equals 9 very easily using the formula. So this is your expression for how to get the probability of at least 10 bankruptcies filed in the course of the year. All right. Hopefully that gives you some intuition or gives you a good refresher on the Poisson distribution. The next distribution we're going to be moving on to is the normal distribution. So what makes a normal distribution kind of cool is that it's found everywhere, right? You might find it in image processing. You might be able to find it in signal processing. You could also find it in various contexts, such as economics. You can also find manifestations of it in nature. So the normal distribution is everywhere, and it's kind of good to get a familiarity with it. So here's how the normal distribution actually looks like. So it actually looks like what's called a bell curve. So you can see it's almost looking like a little hill, right? And at this center point, we're going to have our mean. We're going to call it mu. And basically, this distance here is going to be what's called sigma. So the sigma is going to be the standard deviation or the spread. So every normal distribution, it's continuous, right? As you can see. So we cannot enumerate all possible values that we can find probabilities of on the normal distribution. In fact, let's say we want to find the probability of, a random variable being exactly this value in red. So if we actually if we actually look up here, right? We actually cannot find such a probability of x being a number. So the probability of x equaling a number in the normal distribution is actually 0. We can't really find the probability of, x being exactly one value and only that value in a continuous distribution, right? Think about how many possible values there are to choose from. There's infinite possible values to choose from, especially since the space we're talking about is a continuous space. So we don't really care about finding this in our normal distribution. What we will say is this. We will say that the probability of x, we will care more about finding the probability of x less than or equal to c. So for example, if this is my c right here, the probability of x less than or equal to c will be represented by this area here that I shade in green, right? So we're going to care more about these things, right? This is more important in a normal distribution, right? So the mean of the normal distribution will always be specified, and the standard deviation will always be specified. If you're given the variance, though, instead of standard deviation, all you have to do is take the square root of the variance to get the standard deviation. So we will say that the expected value for a normal distribution is going to be mu, or the mean. We will also say that the variance associated with the random variable x, where x can be modeled by a normal distribution, is sigma squared, right? So that's what we're going to know. So I guess it helps to get some intuition by actually doing some examples. So, one more thing to talk about in normal distributions. Normal distributions will have known probabilities if the mean is 0 and the standard deviation is 1, right? So in your textbooks, you will have tables where if you're given a normal distribution where the mean is 0 and the standard deviation is 1, and I look up a value, say c, right here, right? We will be able to get this area by looking at our table. So I'm going to show you quickly what this table looks like. So here's an example of our normal distribution table. And given a value in this normal distribution, which will have mean of 0 and standard deviation of 1, we can find this area shown in gray. So for example, let's say z here was negative 0.75. So what I'm going to do is I'm going to go into our table and look for negative 0.75. So negative 0.7 plus 0.05 is going to be negative 0.75. So we take basically this row and this column and find the intersections. So you have negative 0.7, negative 0.71, negative 0.72, negative 0.73, negative 0.74, negative 0.75. So the probability of z being less than or equal to negative 0.75 is going to be 0.22663. So this gray area would be 0.22663 if z was negative 0.75. So that's going to be important. But the question is, what if my mean is not 0 and my standard deviation is not 1? What do we do? So what we're going to do is we're going to perform what's called a standardization, right? So we're going to basically take what's called a z-score, right? And to find the z-score, we take x, subtract it from the mean, and we're going to divide by the standard deviation. So what does this all do, right? Well, to take x minus mu, we're going to take the distance between the value of x we care about and the mean of our distribution. So that'll help center around the mean. But when we divide by the standard deviation, what we're doing is we are basically making our spread 1. And we're doing what's actually called a standardization. So this formula will help us convert from any normal distribution to a normal distribution who has mean of 0 and standard deviation of 1. So we're going to use this in handy, and it helps to see an actual example. All right. So example 1. Suppose that we're modeling a distribution of PSI in a car's tire. And we'll use a normal distribution to approximate the PSI of a car's tire. So the distribution has a mean of 33 PSI with a standard deviation of 3 PSI. So we want the probability that a car's tire will have a PSI less than 31, right? So let's see, 1A. we want to find the probability that the car's PSI is less than 31, right? So X will be the PSI of the car's tire, and we want to find this probability. And we know our normal distribution will have mean of 33, and the standard deviation, or the sigma in this case, will be 3. In the case of this problem, our variance would actually be 9, but we're given the standard deviation, so we don't have to worry about finding the standard deviation. It's already in the problem. So what we're going to do is find the z-score, right? So this probability is equal to the probability that z is less than or equal to 31 is the x we care about, 33 is our mean, and we're going to divide by 3. So we're simply concerned about finding the probability that z is less than or equal to negative 2/3, right? And negative 2/3 is approximately p of z less than or equal to negative 0.666. We're going to approximate it to negative 0.67 to make our lives easier. So now we're going to go into our table and look for the z-score of negative 0.67. So we go to negative 0.6 here, and when we go over here, we go to negative 0.67. So this area here is the probability in which z is less than or equal to negative 0.67. So this is our answer, 0.25143. Okay, cool. So that takes care of 1A. We move on to 1B. Anything under 20 psi is considered a flat tire. So we want to find the probability that our tire is a flat tire. So we want to find the probability that x is less than or equal to 20, right? And we know that the mu, and we know that the mean of our normal distribution is 33, and we know that the sigma is 3, right? So we'll take the z-score. So it's just going to be p of z less than or equal to 20 minus 33 over 3, which will be p of z less than or equal to negative 13/3, which is approximately p of z is less than or equal to negative 4.33. So let's see if we can find this in our table. Negative 4.33. Looks like my table doesn't really show that. So I'm going to have to, so what we can do is just, find this probability in your calculator, or what you can do is Google another image of a z-score table to help you find this. But what we care is finding this basically. So you'll have to look up a z-score table and look for where probability of z less than or equal to negative 4.33 is. But this is just giving you the general idea of what to do. All right, part C. So we said that 40 psi or above on a tire is considered dangerous, as the tire could potentially wear and tear. We want to find the probability that our tire is considered dangerous. So let x be our psi. So we want the probability of x above 40, or at least 40, right? Because we want to find the probability that our tire is dangerous, right? So we know that our tire distribution has mean of 33 and standard deviation of 3. So this is going to be the probability of z greater than or equal to 40 minus 33 over 3, which is going to be the probability of z greater than or equal to 7/3, which is approximately the probability of z greater than or equal to 2.33. Right. So what we want to do is find the probability of z greater than or equal to 2.33. So let's look in our table. So let's look for 2.33. But one thing you're going to have to remember is the probability of z less than or equal to a number in this table will be this area here, right? Well, if we draw our distribution, right, we have 2.33 here, right? We want z to be above, so I want to get this red area, right? However, the green area right here is what our table is giving us. So how can we find this red area right here? Well, all we can say is that we want to subtract out this green area. So, but what do all probabilities sum up to? All probabilities sum up to 1. So the probability of z greater than or equal to 2.33 is going to be equal to 1 minus the probability of z less than or equal to 2.33. So this is going to be the green region right here. and this term right here is to find, right? So let's find the probability of z less than or equal to 2.33. So if we go into our table, we see 2.33. That's going to be 0.99010. So basically the answer will be 1 minus 0.99010, which is somewhere around 0.01. So it's a very small chance, basically, what we're seeing here in this distribution. Okay, so that takes care of problem 1c. So we move on to example 2. Example 2 is going to be a little bit more involved, but we'll see. So suppose that we're modeling the distribution of salary bonuses at a company. We approximate this distribution as a normal distribution with mean 20,000 and standard deviation 5,000. And what we know is that Bob's bonus is higher than 20% of his coworkers. So given this information, let's approximate what Bob's bonus is. Okay, so we know the bonuses lie on a normal distribution, right? And say Bob's bonus was here, right, at X. If Bob's bonus is higher than 20% of the coworkers, then basically there are 20% of coworkers who made a bonus less than Bob. So this area right here is actually going to be 0.2. And what helps with understanding these normal distributions is actually to draw out the distribution and shade in the regions that you know and what regions to find. So the approach will come to you that way. So we want to find basically the probability of z less than or equal to some number and have it go to 20%. So what we're going to do is we're going to look in our table, right? And look in these cells here and look for a value that is close enough to 0.20. So if we look at our table, we'll see right here, we're having a 0.20045 versus a 0.19766. It seems like this value here is much, much closer to 0.20 than 0.19766. So I'm going to use this as our approximation of 20%, right? So this gray area is going to be 20%, which can be approximated by whatever z-score corresponds to this region I'm hovering over. So that z-score happens to be at negative 0.84. So basically, C will equal negative 0.84. So this is the target z-score, right? And what do we know about z-score? We know that the z-score is the x value minus the mean over the standard deviation. Now let's look back to see what other givens we have. We know that the mean is 20,000, and we know that the standard deviation is 5,000 right here. So mean is 20,000, standard deviation is 5,000. So negative 0.84 will equal x minus 20,000 over 5,000. So then all we have to do is solve this equation for x. So x will equal negative 0.84 times 5,000 plus 20,000. So this should give you an approximation for Bob's bonus, this formula right here. So you can punch this into your calculator and get an approximation for Bob's bonus. So that's how you do problem 2. One more thing I'd like to reiterate on is, suppose we want to find the probability of, say, I don't know, 31 less than or equal to x less than or equal to 33. And we're going to use the car tire example. We're going to jump back to that a little bit. So then we use 33 and sigma is 3, right? So when we have compound inequalities, let's convert this problem to a z-score problem. So we want to find the probability of 31 minus 33 over 3. So that's going to be the z-score corresponding to 31. And this is going to be z. And the z-score corresponding to 33 is 33 minus 33 over 3. So we want to find this probability. So negative 2/3 less than or equal to z less than or equal to 0. So we can actually break up this inequality a bit further to make our life easier. So if you think about our region, right? If this is our bell curve, right? Here's my z-score of 0, and here's my z-score of negative 2/3, right? our table can tell you the probability of z less than or equal to 0, which is the red region, and it can also tell you the probability of z less than or equal to negative 2/3. That'll be this green region. But what if we want the area in between, right? So that would be this yellowish region, right? So what we can do is subtract the red region area from the green region area. So we can just simply do this. This will just simply be p of z less than or equal to 0 minus the probability of z less than or equal to negative 2/3. And I'll note this as the red region, and this one will be the green region. So we're subtracting the red region minus the green region to get the yellow area, which is the area we desire, right? So let me mark that in yellow. So we want, oh, sorry. So we want, this is the yellow region we care about, basically. So let's take the probability of z less than or equal to 0. So we go to our z table. Okay, z is less than or equal to 0. Okay, that's 0.5. And it makes sense because the normal distribution is actually symmetric. So it's kind of a cool property to know. So this will be 0.5 as the red region. The green region, let's look for the probability of z less than or equal to negative 2/3. So negative 2/3 would be negative 0.67. So the z-score course, the area of the region would be 0.25143. So the green region would be 0.25143. And we're going to subtract these two, and this will be our probability of negative 31 less than or equal to x less than or equal to 33. So yeah, that's just a way to work with compound inequalities with the normal distribution. Hopefully this video gives you a good refresher on your basics of probability distributions, especially the binomial, Poisson, and normal distributions. Thank you for tuning in, and looking forward to seeing you in the next video.